Now, some sequences do not have a simple defining formulas like the ones we found for this example and for this example. So some sequences can have that the nth term in the sequence can depend on previous terms. So, for example, I can have a sequence such that the first term is 2, and then I can say that the next term is going to be the previous term, 2 plus 3, for example. So A2 depends on the previous term, is going to be A1 plus 3. And then what's A3 going to be? Well, it's going to be the previous term, so A2 plus 3. So in general, the term an is going to be the previous term, which is an minus 1. The previous term has a 1 less than n, plus 3. So this is an example of what we call a recursively defined sequence, where the general term depends on the previous term. A famous recursively defined sequence is the Fibonacci sequence. So the Fibonacci sequence is defined by the first two terms are 1, and then the next terms are the sum of the previous two terms. So this depends on 2 of the previous terms. So let's see what that means. So f1 is 1 and f2 is 1. So this is given to us, and then we are given that the next term is the sum of the previous two terms. So fn minus 1 plus fn minus 2. So that means that f3 is going to be, so when n is 3, f3 is going to be f2 plus f1. So the sum of the previous two terms, so it's going to be 1 plus 1, which is 2. What about f4? f4 is going to be the sum of the previous two terms, so previous plus previous. So it's going to be f3, which is 2, plus f2, which is 1. What is f5 going to be? The sum of the previous two terms, so f4 plus f3, but f4 was 3 and f3 was 2, so it's 5. f6 is going to be f5 plus f4, f5 was 5, f4 was 3, so 8, and then f7 is f6 plus f5. And f6 is 8, and f5 is 5, so this is 13. So the Fibonacci sequence is the sequence where the first two terms are 1, and then the next term is this addition of the previous two terms. So it'll be 2, and then, well, I already have them in here, but you can get them always by looking, what's the next term? Well, the next term is 1 plus 2, which is 3. What's the next term? The next term is 2 plus 3, which is 5. What's the next term? The next term is the previous two terms added together, which is 8. And then what's the next term? 5 plus 8, 13. What would be the next term? 8 plus 13, 21, and so on. So this is exactly what we got when we actually used the formula. But the formula just means add the previous two terms. So there are sequences that are defined in this way. And you will learn in Calc 2 how to find, if you're adding, this takes us to the next thing. If you're adding the terms of a sequence, you obtain what we call a series. So let's see what we mean by that. So if we add the terms of a sequence, we obtain a series. So if I have a sequence, the sequence which is A1, A2, A3, A4, and so on. So a sequence, remember, it's an infinite list of numbers. If I add them, then I obtain a series. So a series is going to be A1 plus A2 plus A3 plus A4 plus dot dot dot. I'm adding all the terms of the sequence. So that is called a series. So the series is going to be an infinite sum of numbers, and this sum, or adding, may add up to an actual value or not. So you'll see in Calc 2 that you'll talk about the series converging or diverging. So for example, I can have that the series a1 plus a2 plus a3 plus a4 plus dot dot can add up to a single value if I call it S. So it can add up to S, then we say that the series converges to S. For example, let's look at your number 4 on page 1. So number 4 on page 1 was this sequence. You had the sequence 1, negative 1/2, 1/3, negative 1/4, and so on. So if you look at the series, so the series is going to be adding the terms of this sequence. So it's going to be 1 minus 1/2 plus 1/3 minus 1/4, and so on. You actually learn in Calc 2 that this is ln of 2. So you don't need to know this right now, but I'm just saying that this is going to add up to a single value. So we're going to say that this series converges to ln of 2. But there are some series that diverge. For example, if, well, you'll see more in Calc 2. All right, so, however, if we have a finite series, or we call that a partial sum. So if I have the sequence a1, a2, a3, a4, and so on, so this is the sequence. If I look at the sum a1 plus a2 plus a3, this is a finite sum. It's a finite sum, and it's called a partial sum. I'm not looking at all of it, a1 plus a2 plus a3 plus a4 plus all the way. I am looking at a partial one, a1 plus a2 plus a3. This is denoted to S3. If I'm looking at a1 plus a2 plus a3 plus a4 plus a5, this is another partial sum and is denoted with S5. So you're going to use this for Calc 2 when you learn about series. These are called the partial sums of the series, and they're going to become important there. So the key in here is to recognize that I can evaluate, I can find the sum of partial sums always, because it's a finite sum. But for infinite, I can't, like sometimes I can. You'll see for telescoping series and geometric series, you'll be able to find the actual values. But if you're looking at a partial sum, you can always find the value because, for example, find the sum, if an equals 3n plus 1, what's going to be S3? The partial sum. So adding the first 3 terms of the sequence. So it's going to be a1 plus a2 plus a3. So it's going to be, so S3 is the partial sum corresponding to adding the first 3 terms of the sequence. And the sequence is given by this formula. So what's going to be a1? Well, it's going to be 3 times 1 plus 1. That corresponds to n equals 1. It's going to be a2. It's going to be 3 times 2 plus 1. Plus, what's going to be a3? It's going to be 3 times 3 plus 1. So see, this is a number that I can actually calculate. This is 4 plus 7 plus 10. So this is 21. So I can always find the value for partial sums because it's a finite sum. It stops. I'm only doing 3 of them, or I'm only doing 5 of them. But for an infinite series, you'll learn in Calc 2 how to find the actual value of the series if it exists. So one thing that I do want to point out is this notation. So I don't know about you, but it can get tiring having to write all of this, like A1 plus A2 plus A3 plus A4. So basically we're going to have a shortcut how to write this by using what we call sigma notation. So sigma is the Greek letter like this, sigma. And on the bottom, you're going to say that your n starts at 1 and then you're going to give it the a-nth formula. So this is just a shortcut. Instead of writing a1 plus a2 plus a3 plus a4, we usually put an infinity of the top if I'm talking about an infinite series, or if I'm talking about a partial one. For example, in here, I'm going to say that a1 plus a2 plus a3 plus a4 plus a5 is summation, so sigma from n equals 1 to where? 1, 2, 3, 4, 5 to 5 of an. Okay? So this is the same as writing this, but it's short. It's a shortcut of writing it. So sigma just means add all these up. So when n equals 1, when n equals 2, so a1 plus a2 plus a3 plus a4 plus a5, stop there. If you're looking at an infinite series, when you're adding infinite many terms, you're just going to say that this is summation from n equals 1 to infinity of an. So instead of writing all of this, you would write this. What would be the sigma notation for this one, a1 plus a2 plus a3? Well, it will be just sigma from n equals 1 to 3, because I'm adding just the 3 first terms, so an. So sigma notation is just saying that you're adding. This means add them all up for all of these n's. So let's see. So, for example, for this one, if I wanted to look at the series, you would say that the series is from n equals 1 to infinity of 2n minus 1. So this would mean add a1 plus a2 plus a3 and so on. So if I put in what a1 is, this will mean add 1. a1 was 1, plus a2 was 3, plus 5, plus 7, and so on. So this is just a shortcut. Sigma notation is a shortcut. I don't want to be writing all this or all this. I'll just say in a compact fashion, this series is this. All right, we will talk more about sequences and series in this chapter. Specifically, we'll look at arithmetic sequences, geometric sequences, and then series. All right, so we will stop here. So exam 3 is going to cover chapter 10 and 11 and this first section from chapter 12.